Exploration.
Hi, everyone. So back to the ocean. First of all, I want to give a shout out to Anna for the invitation to be here, and around all this inspiration is very catchy. So I want to. I had a very academic type presentation, but after sitting through the last day and a half, I changed it to be more storytelling. So that's what you're going to get. So I hail from Woods Hole Oceanographic, and as a kid, I grew up in Barnegat Bay, New Jersey, down the shore they call it, and there, that's where I learned my passion for the ocean and marine science, and the little investigator curiosity grew there by hunting and gathering and crabbing and fishing with my family and grandparents. And also during that period, when I was 5 years old, my grandpa taught me how to tinker on two-stroke outboard engines, old Evinrudes. Little would I know that 20 years later, I would end up working with autonomous underwater vehicles known as AUVs. So this picture here, I'm holding a Remus AUV, and AUVs tend to be classified according to their size, like small, medium, large. This is one of the small ones that is known across the military and industry as the two-man portable. So when I look back at this picture, it's pretty, it grounds me and reminds me of the journey and the importance of innovation and pushing the envelope forward, but more importantly, to be a role model and mentor to the underdogs and women and minorities that we need to recruit and inspire in STEM fields. So that's really what motivates me every day to do what I do. But before working with autonomous underwater vehicles, I got my start in biology, and I have a kind of an untraditional path, starting out with biology, environmental policy degree, and somehow I ended up with underwater robots. So I'm going to tell you a little bit about that journey. But I started out studying zooplankton and plankton in a biology lab at Woods Hole. And I worked for a scientist who was a bit of a tinkerer. And one of my first jobs was to learn how to use Sea Rover, which is this remote operated vehicle here, which has a tether and real-time video back up to the ship. And I was scared half to death. I had no robotics training whatsoever. So I had just come back from Antarctica, all banged up from being in the ice, and I had to put it back together and then go use it in Antarctica in the spring of 2002. Sure enough, we go down there, and we were studying the overwintering patterns of euphausiids, which are Antarctic krill. And the ROV got all beat up, and although I was scared to death, I knew what I was doing. I had some help when I was able to put it together. And it was in this moment, in this journey of being in this beautiful place, Antarctica, right after 9/11, for nearly 2 months, and then being thrown into robotics. And this was the first introduction I had in engineering and robotics, and the rest is history. So I want to talk a little bit about the comparison to space and the ocean. So I think that there's one really important similarity between outer space and the ocean, is that we can look out and stare and gaze into both and be completely mesmerized. But one major difference of the ocean is that there's this opaque layer and this curtain that you just can't remove. You can stare out into the horizon, but you don't know what lies beneath. And then you add a bunch of icebergs and sea ice, and it gets even more complicated. So that's where robots come in. And so most of the robots that I work with, they're AUVs, they're torpedo-shaped, and that's so they can be really efficient swimmers and hydrodynamic. They're extensions of ourselves. They go where people can't. They're typically pre-programmed with a set of instructions, and they've evolved over time to think on their own. And they're like underwater aircraft carriers, so they can navigate, go where you want them to go. Some of them have propellers, some of them have wings, and they can carry sensors like multi-beam sonar and make bathymetry maps. They have side-scan sonar for doing large-scale surveys, looking for lost shipwrecks, airplanes. We do underwater docking and recharging, fisheries surveys, and I've even used an AUV to inspect the New York City aqueduct that was leaking a lot of water back in the early 2000s, in 2004. So But what I want to talk about is some of my current initiatives and my latest uh, exciting news to report is that I've started this new lab called Cybotics. Because while I was working with the REMIS AUVs for a long time, about the first 10 years of my career, and that picture that I showed you holding the two-man portable REMIS was in a military exercise called AUV Fest. And what happened there is I learned a ton, and I was working with Navy SEALs and working on covert operations and SEAL delivery vehicles. And we were doing all this neat stuff, but I couldn't talk about it. Everything was classified or sensitive. And I really like being a storyteller, and my mission was to really inspire the next generation. So that's where Cybotics comes in, where we actually do a lot of innovation. We develop robots, sensors, the behaviors or software that allows sensors to run, but also what do you do when you observe something in the ocean. But we also are huge, outreach and educators to teach people what's possible with underwater robots. So the first thing I like to tell scientists or anybody who wants to learn about robots is that their problems and challenges are actually opportunities for robots. And it's interesting because what we do is really hard with underwater technology, but I feel like one of the biggest challenges is actually convincing scientists to use robots that they have less control over. Because traditional oceanography happens when you go out in a large research vessel, you're towing behind it, towed sleds with all kinds of sensors, the same that you can put on an autonomous vehicle. And people have this connection to the sea, they want to be there. So it's hard to convince folks to be shipless, be completely autonomous, let it go, and let the robot do the work for you. But robots are not without drama either. So what we do constantly to be successful in the ocean is to think about all the things that can go wrong. And oftentimes things go wrong, but not the thing that we thought that was going to go wrong. So here's 3 examples of things that were unexpected. So here, this is a REMIS 600 vehicle that we're using as a shark cam vehicle following great white sharks in Guadalupe Island. And it was following the shark, and the shark, I guess, had a sense of humor and went into this cave, and shark cam followed it in and got stuck. So we were able to figure out where it was within about 25 meters, but we didn't have the tools to go in and rescue it. We would have needed an ROV. So it took 40 days, 2 expeditions, my Christmas, my New Year's, to rescue it, but we did, and it has a happy ending because we thought about backup transponders and emergency location devices to locate it. And then, of course, there was the 65 times or so that we were attacked by great white sharks. And I have to admit, it was unexpected because the first time we tracked a white shark, it was in Cape Cod, and the shark showed no interest whatsoever in the robot. We'll talk more about that. But we survived, knock on wood, every single attack. And then there's this one here. There's a little bit of Photoshop going on, but it helps with the story. We were mapping out a melting glacier in Greenland, and we were acoustically tracking it. So we had a buoy with acoustics that was talking to the vehicle. We're on the beach, and freewave radio was giving us positions of the vehicle, and then we stopped hearing from it. About 2 hours later, I got a phone call on my Iridium phone from the robot giving me its latitude and longitude, telling me where it was. We get in the boat, we head down the fjord, and it was out to sea, and it had jumped out of the water and landed on a floating iceberg. And it would have been gone if we didn't have the Iridium backup systems. So now I want to move on to one of the biggest, crises before us, and that is the melting of ice up in the Arctic. So this is the Northwest Passage, which is now becoming open to the point where commercial vessels and private vessels can now navigate through the Northwest Passage. So in 2016, the first commercial cruise liner, the Crystal Serenity, did its maiden voyage carrying more than 1,000 people through the Northwest Passage. And the US and other Arctic nations realized that they didn't have the tools and the infrastructure in place to rapidly respond if we would have a modern day Titanic before us. And at that same time, Shell was up there about to drill. And so there was a funding opportunity through the Department of Homeland Security, where the Coast Guard falls under in the US. and there was a project that started to figure out how to develop technology, a robot, likely a robot that can be dropped from a helicopter, navigate under ice, collect data, stay there for a while, because once you put something in the Arctic, it's really hard to get it back for harsh weather conditions, and so oftentimes people will put their robot out and they don't get it back. So I started on this mission to do some research and to what it would look like to have robots up in the Arctic. And there's a lot of graphical representations of what a networked ocean in the Arctic looks like. But there's very little literature on people actually deploying robots and having success and learning from other people's missions. And so there's only one way to do it, and that's to learn by doing. So my first ice expedition was actually on shore-fast ice in Barrow, and it was back in 2010. And the idea was to build a camp, a science camp, that we would work out of, and we put a hole in the ice, put up a tent and a gantry, and we would be deploying a Remus 100 to go out 10 kilometers, swim back, hit the hole, recover it from that, and it was studying the physical oceanography features of the choke point of the Chukchi Sea. Piece of cake, right? But what we had to do was like a week's worth of forging a path to be able to drive our snow machines out there to work on the camp. And we had just gotten back from setting up the camp, and one of the locals, our guide, rapidly grabs the snow machine and a sled, attaches it, heads out, and we're like, what does he know that we don't know? He comes back about a half an hour later with some shreds of our tent and the gantry, fortunately, and apparently the wind and the current had just changed direction. It's not like he had, an iPhone and was looking up the currents and the weather. He just knew it. He sensed it. And a big ice flow, like the size of New York State, had just like crashed up into our ice flow. And this is what happened. And this is literally like, these are our snowmobile tracks you can see right here. And they're about 50 feet high. So I don't have any near-death experiences, just some near misses to talk about, fortunately. And somehow we keep going back and doing more. So now the big project is all around rapid response to oil spills in the Arctic. And oil spills are a proxy to actually study lots of different things, like harmful algal blooms, dioxins in the water, and eDNA, fisheries surveys, like you name it. So everything that we're developing here can be applied to other things. So what we're tasked to do is to find a really special robot that can go for a long period of time, be propeller driven, be able to dock under ice, be able to communicate all its data without surfacing. So we developed a networked Arctic buoy system, and it had to be able to drop out of a helicopter. So we started out and we collaborated with MBARI, and we chose the long-range AUV, which is originally developed at MBARI, and we adapted it to be an under-ice vehicle. And that meant that we had to be able to navigate potentially relative to the underside of the ice, to the seafloor. We needed to be able to get deployed, fall out of a helicopter, still be operational, and then navigate to and park and attach to a cable that's hanging down from a buoy, and then acoustically send data packets back through the buoy, through Iridium, back to command control. And you can literally do all this from your cell phone. So that was our mission. And the most important part why LRAV is really special is because of its long-range capabilities. So all other propeller-driven AUVs can go for hours to days. They have really fine scale resolution and can do lots of amazing stuff, but they have rechargeable lithium-ion batteries, and that's its biggest constraint. So with LRAV, much like the balloons we heard about yesterday, they have a variable buoyancy system, and they have a mass shifter so they can move their batteries fore and aft and not have to use their propulsion system and go into a low power, drift mode, and hover. And so its max range, its max mission so far has been 1,800 kilometers. So that's like, the average mission is around 1,500 kilometers. So here's Woods Hole, where I am, and you can literally launch it from the beach to Bermuda and still have a few days of juice in your tank, which is a game changer for even open ocean science in terms of multi-mission capabilities. So here's another challenge in terms of developing oil spill technology is that how do you develop all these sensors and behaviors and not have oil to test your simulation in? So we work with NOAA, and there's a bunch of shipwrecks as part of the Roulette program, World War II shipwrecks that are heavy leakers. So the way we program the vehicles to put in a bunch of waypoints and drive the vehicle south of the shelf break and survey and test our algorithms to see how well things work. So it's just like putting in a bunch of, like I said, cookie crumbs, and that's how we navigate using a whole bunch of different sensors. When we don't have oil, we use harmless dyes like fluorescein to create a test area. And another issue that we have is we have one tiny vehicle to be able to do, oftentimes only one vehicle to survey a large area. This is 100 feet by 45 miles long. It's an oil slick in the Gulf of Mexico. So we really need to scale up our ocean research dollars to push the envelope on scalability. So one more thing that we're always tasked to do, like space exploration, we don't have always don't have the right sensors to do the job. So in this case, EPA wanted to be able to take water samples that were devoid of any hydrocarbons, and they wanted to measure VOCs, volatile organic compounds. So I conceptualized a water gulping system, much like a six-pack of beer, and that was modular. I can go from vehicle to vehicle, so then you can navigate, find an oil spot using other sensors, a hot spot, and then suck a sample, and then take it back to the lab. So now I'm going to switch gears and talk a little bit about charismatic megafauna. So back in the late 2000s, when small, cheap cameras like GoPros came out in the market, we always, before that, had this way of always looking downward at the seafloor with autonomous robots, making maps and looking for mines and things. But I started putting GoPros looking backwards, and it turns out that the vehicles are fads, or fish attraction devices, and all kinds of things were following behind us. So then myself and a bunch of engineers developed SharkCam, which is the world's only 3D tracking filming robot. And with that, we're able to get fine-scale resolution tracks over a short period of time, getting where the animal is in its environment, how it's operating within its environment, interacting with others, and also high-resolution video. So the idea behind this is that you have a lot of tags that are satellite, and you get little cookie crumbs of where they go, but you don't know what they're doing when they get there. So this is an opportunity to use this technology to show us what they are doing when they arrive. And it works like the most advanced game of Marco Polo you've ever played. So we tag the animal, and then the vehicle is told where the animal is, and it pings it acoustically, and then the tag responds with 2 pings, and it can figure out the bearing, the range, and the depth of the animal by using acoustics and hydrophones on the vehicle. So I'm going to leave you with one thought here before I show you a video of some of our highlights, is that every time we put the vehicle in the water, we learn something new. And like here, you can see a great white shark down at 200 meters, swimming in a catatonic state with its mouth wide open, swimming into a 2-knot current. And no one's ever documented that before. So, all right, so sit back, and here comes the video. Little help. Thank you. So I'm way over, so that's probably a good way to end. But I did want to say, I guess every time we put, like I said, every time we put a vehicle in the water, we learn something new. And compared to space exploration, which gets 150 to 1 times the funding of ocean exploration, we have a lot to worry about on our planet. I was going to read a doom and gloom quote, but I'll leave that out because we've had enough of that today. But yeah, we need the ocean. Every breath relies on it, and I'm really happy to be here. And thanks for your attention.
Thank you.
Thank you very much.